Welcome to this Lumi Roadshow. This event is targeted in particular for the potential end users and other stakeholders of Lumi Supercomputer in the capital area, Finland. This event is organized by CSC IT Center for Science, and my name is Juhani Huttunen, and I'm acting as a project manager of Lumi user program. Lumi Supercomputer is the new European flagship computer that will be located in CSC's data center in Kajaani in Finland. The purpose of this roadshows and Lumi user program is to create awareness and share information of the opportunities that Lumi will bring to research, development and innovations for various user groups, varying from academic research, applied research, up to commercial company activities. We also like to hear about your needs and expectations for Lumi, so this can be used for service development of Lumi supercomputing environment. Let's have next a look some meeting practices, because we are locally here in Espoo and this is streamed over the web. So all participants over web are muted in the beginning, and if you like to ask clarifying questions, please push a raise hand button at the bottom of the Zoom screen, so the auditors can then give you an opportunity to speak. There is also a question and answer window at the bottom of the Zoom screen, so you can write throughout this event your questions there, and we will answer those at the appropriate time. There's also a chat window that can be used to converse with the host organizers and give some information also back to you as needed. Please note that this event is recorded, and there is also the Twitter account information at the bottom of the slide. Our interesting agenda today is the following. First, Pekka Manninen, director of Lumi's leader supercomputing facility, will tell you everything essential about Lumi supercomputer and its ecosystem. After that, we have a 15 minutes break, and the next presenter of this morning is Milica Todorovic from Aalto University, giving a researcher's perspective of supercomputing and her research area. After her presentation, we have a half-an-hour discussion session reserved in particular to answer your any kind of questions related to Lumi. And then we close with a lunch break, and those who have pre-registered to have one-to-one discussions with us can have an opportunity in the afternoon private sessions. So this is our today's agenda, and let's give a stage for Pekka Manninen, director of Lumi supercomputing facility.
All right, good morning also on my behalf. And today I'm going to shed some light on the upcoming Lumi supercomputer system, and perhaps some background information on about the story of it. And indeed, let's review the last 2 years, how we have come to the stage where we are able to give a user program or like give a roadshow about the system. So a long story of Lumi and the EuroSPC initiative. And then after that, we want to go to the kind of like a main point of the seminar series is the what opportunities and benefits Lumi supercomputer or supercomputing in general can bring for research, development and innovation in Finland and in Europe. And the third part would be more technical one, targeted for the end users that will be really hands-on using the system. So how should one prepare for the upcoming leadership class supercomputer Lumi? Like Juhani said, we will have a dedicated session for questions and answers, but we can take the burning questions at the end of the talk using the methods instructed in the beginning. So over Zoom or locally here in Espoo. Okay, let's get started. So EuroHPC. And the story of Lumi begins roughly 2 years ago, a bit more than 2 years ago, when European Commission woke up to the fact that Europe is behind China and US when it comes to the capabilities in cutting-edge data management and computing. And to bridge that gap, an initiative called EuroHPC joint undertaking was formed, and as a joint effort of the Commission as well as member states to pool resources to develop a world-class infrastructure for data and computing. And the infrastructure is complemented with an research and innovation agenda related to this area. And EuroHPC has really gotten good momentum, so it has a multi-billion budget for many years, and also the countries have found it beneficial, and already 32 European or Union countries and associated countries have joined the joint undertaking. And the progress of the EuroHPC has been fast so far. So the first generation systems was already announced in the summer of 2019. And this generation consists of 3 of these leadership class supercomputers they call pre-exascale, that were designed to locate in Finland, Italy, and Spain, and 5 smaller but not small supercomputer systems on elsewhere. And the program will continue in the future with the second generation planned sometime in the 2024 time frame, and even the third generation of systems sometime in 2027 perhaps. But to Lumi, which is the EuroHPC system in Finland. And one important and a novel theme of Lumi is that it's in Finland, but it's not a Finnish system. So Finland is funding it, but it's a joint effort of the Commission and 10 countries on the that we call Lumi consortium. And in this consortium, all the countries are investing major amount of money for an acquisition of one supercomputer that we have. The consortium has decided to put in the CSC's data center in Kajaani, in Finland. And the idea is that none of the stakeholders have dedicated resources or dedicated hardware on the system, but the computing cycles of Lumi will be allocated per the investment into the system. And as the system is, the total cost of ownership of this system is one half funded by the EuroHPC joint undertaking. So one half of the resources and the cycles of the system will be allocated by the JU, and it's like something nowadays known as praise will be the highly likely choice for the who's going to be doing this peer review access on these resources. And the remaining half will be allocated by the Lumi countries by local considerations and policies. And they are, for many of the Lumi countries, they are extensions for the national resources. They have the national, the HPC resources each of this country have to provide locally. And the key reason why it was chosen to be in Kajaani is that it's not very far-fetched to say this is one of the best locations in the world to host large-scale supercomputers. And the data center itself is in a former paper factory. So the forest giant UPM shut down the paper machines in mid 2008 timeframe, and since 2012, CSC has operated its the Finnish supercomputers on that site. And at the moment, Lumi will be on the main hall of the of the factory that's used to be just an empty huge industrial hall with the paper machine demolished. But in a short time frame, or sometime at the end of the year, there will be, and this kind of a building within a building we call the Lumi data center will be on the end of the one of these halls. And the key specs of the data center are very impressive. So we won't be running out of power. The electricity is very reliable because the paper machine just couldn't consume a lot of energy and it couldn't go down. Due to the cold climate, we can do free cooling throughout the year, but instead of wasting the heat to the outside air, we are going to collect it and then use it to heat up the surrounding city of Kajaani, consisting of perhaps 20% of the energy needs of the heating energy needs of the city. And with this thinking, we can say that Lumi is not only carbon neutral, but it also reduces carbon emissions because of this capability. It may be remote, but it's very well connected, and as a robust industrial site, we have no problems on running the most secure environment for IT. But that was the Lumi story. So what has happened during the last some years? We are basically through the procurement of the system, and now we are happy to announce the specifications of the system. And Lumi we run on competitive dialogue procurement, or the EuroSPTJU run the procurement. We were helping them. The consortium was helping them, and the winner of this procurement, the competitive procurement, was HPE, with an offering a Cray EX supercomputer as a solution for Lumi. And specification of Lumi is that it reaches an enormous computing capability of 550 petaflops per second for the GPU partition, and it's going to make it one of the fastest at the time of the installation of the system. And put in perspective, the fastest supercomputer today, so just yesterday the top 500 list was announced. So the fastest today is Fugaku in Japan, with peak performance, which is smaller than the upcoming Lumi performance. And also the gap to the second fastest supercomputer today, which is the Summit in the US, is supposed to be pretty large, over two times the speed of Summit. So it's going to be a very fast system, even if the installation is still quite far away in time. And then again, they of course, well, not of course, but it's unlikely that it will be the fastest anymore until the time of the installation. But there will be some other leadership systems getting to the same list. But nonetheless, so just like given perspective, what does 550 petaflop mean? Another way of looking at what does 550 petaflop mean is just if you try to reach the same computing power, you would need a 1.5 million powerful laptops, which would be a tower of over 20 kilometers high, tower of laptops. Of course, Lumi won't do the job of the 1.5 million laptops, or vice versa, so the laptops won't do the same job as Lumi is doing, but just giving us some kind of an idea what kind of a number crunching power we are talking about. Even if the capability of the system, it's a very engineering feat that the system is quite compact. In fact, it's the size of roughly of a tennis court. But in any case, what is the most important fact for the end users is that it's going to be very modern and very powerful platform for high performance computing, artificial intelligence, data analytics, and of course the fruitful cross-cutting of these domains. And to be a little bit more technical, specific, I would like to go through the architecture of the system. And like I said, it's an GPU accelerated supercomputer meant to support the convergence of the realms of HPC, AI, and SPDA. And the architecture is that the system consists of different partitions that are, however, seamlessly interacting. So all these partitions are available from the same user environment or computing environment, and they see the same storage capabilities. And also, in fact, it's also possible to combine different these resources of within the system into the very same workflow or even very same job or like a program binary. And the computing capabilities of the system consist of the towering GPU partition that gives the 550 petaflop, and the technology there is we ended up selecting AMD Instinct GPUs for multiple of reasons. And it's supplemented by an CPU partition or more traditional x86 technology, also provided by AMD processors. So AMD EPYC processor of roughly 200,000 CPU cores. So would be a big supercomputer of its own, but here it's a kind of like a supplementary resource for the Lumi system. Also, it has capabilities special capabilities for data analytics, visualization, pre and post processing, meshing in memory databases, and so on, via something we call data analytics partition, which is essentially a very large shared memory system with the latest graphics GPUs. In addition, there will be some supplementary cloud computing resources, but in essence, Lumi is really meant for the convergence of cloud computing and bare metal high-performance computing. So it will be more or less cloud-based platform at the end of the day. And if the computing resources are something we could consider leadership class world-class resources, the storage shouldn't be anything behind. So the storage is consisting of 3 tiers, I would say. So there's a pool of accelerated storage, so flash-based technology that reaches a very large bandwidth from the disk to the memory of the GPUs, reaching something like 2 terabytes per second, and very high capability of handling I/O operations. The kind of like a main pool of storage resources is more traditional parallel file system based on Lustre technology of 80 petabytes in size, and also very high read and write bandwidth. And these like a more computational storages are complemented with a service for staging in, staging out data, storing it, sharing, and so on, based on Ceph technology and more familiarly object storage technology. And on the gray on the last branch of the snowflake is something we called LumiQ, which indicates an aspiration for availing also emerging technology platforms on Lumi, even if they are not part of this SPE contract. But it's something we can build to the environment later on. So this is Lumi, pleased to introduce. And so when this all is available, like I mentioned, the snowbank or the data center will be ready at the end of this year. So the installations can start on springtime. And we target that the first phase of the system would open up next summer. And the first phase will consist of everything besides the GPU partition. So all the other crunches besides the GPU partition, and it will come with kind of an early access platform. So an GPU partition with previous gen technology. In fact, that's announced yesterday in supercomputing, and then so it's a platform for doing already science, but also it's a kind of something to stage up to the system in its full glory. And the system will be in its full glory, so this is going to happen at the end of next year, end of 21. The Lumi system should be in its full steam. And the system will enroll to the glorified top 500 list of supercomputers 1 year from now. So the November 2020 list was announced yesterday, and on exactly 1 year from now, Lumi will enroll to the top 500 list. And at that point of time, like I said, would be the fastest if it enters it today. But as there's 1 year to go, it's unlikely it's going to take the top spot of the list. It's going to be on the of course on the very the brightest top, perhaps within the top 5 systems. But where we do want to be, and I think which matters even more for us, is the user experience, and we want to be the leading system when it comes to the innovation on the user environment and the user experience. So, for instance, we are working already along multiple streams here to improve or kind of just like make new innovation. What comes to the what means the HPC system in this decade? Well, the one thing that we think is to allow multiple ways of working on the system. So, of course, we want to provide the traditional command line interface, but in addition, to complement that, there will be high-level interfaces, graphical user interfaces for the resources based on, say, notebooks, RStudio, and the like. And then one thing is that we want to design the software stack to be very much up to date and meet the needs of the large user base coming from the Lumi consortium countries and elsewhere in Europe, with community and commercial software alike. And in addition to the databases and software typically seen on systems, we are working on a concept of datasets as a service, where we provide reference data sets as created and are readily available on the system. We work on different teams on interactive supercomputing, and last but not least, the Lumi comes with a very highly skilled and very extensive and exhaustive form of doing user support based as a 10-country collaboration. So we have a really nice opportunity here to harness and pool the competencies across the 10 countries with very credible HPC centers to the benefit of the whole user base, to basically just pool and share of the different competencies in Europe. And the other thing we think going to be bringing added value and maximize the return of investment of this system is that we have high hopes that the enterprises and the commercial R&D will find these systems useful and important. And in fact, up to 20% of the capacity is something that we could give for industry and SMEs. So, and of course, the idea here is that the world-class HPC resources and the convergence of the high-performance data analytics, AI, and an HPC in the same platform will be something that's just like gives a value add for the R&I in private enterprises. And not only the system, but also the collaboration or private public partnerships, collaboration with academia and industry is something that we think will be a key for the competitiveness of the European industry. So in case of Finland, the modus is that Business Finland will treat these resources as an funding or the innovation funding it can broker to the companies, especially here in this case, they are looking in the beginning SME and small companies that will get the benefit of getting these valuable computing resources for free and not having to buy them from cloud. And also the industries can join the academic open science academic project as long as the IP is most of the IP will be published in peer-reviewed journals. And so we hope to catalyze the industrial R&D with Lumi, but also the international collaboration of Finnish researchers. And I would assume that other Lumi countries think along the same lines. So this is a Finnish perspective for a Finnish end user roadshow. But if there's anybody watching it outside Finland, of course this is this same scheme applies also for the other Lumi countries. And this is an asset that can be, or we hope the Finnish research groups use for making recruitments, so finding good postdocs, good PhD students for their positions, just as an attract with the major share of HPC leading cutting edge HPC resources. Also to build up collaborations in multinational EU research projects and alike. Also to use the platform as Lumi platform as a platform for collaboration. So joining the same projects, sharing data, working together, and so. And last is that the support model that is based on the distributed support team over the consortium is that something we hope that we can bring value add for the Finnish researchers. That's something that we at the moment cannot provide from CSC. And how Lumi fits into the Finnish ecosystem is that, well, as a first notion, I think we are enrolling a golden age when it comes to the Finnish scientific computing, because at the same time we have an ambitious and an up-to-date national computing infrastructure we call DL 2021, datan ja laskennan kehittämisohjelma. That is now more or less ready with the inauguration of the Mahti supercomputer last summer. And it consists of the Puhti and Mahti supercomputers and the Alas data platform. And we think this is kind of like a workhorse for Finnish scientific computing. So more or less all use cases besides the kind of a tip of the iceberg, what we call tier 0 computing projects. And Lumi will bring now the national capability for granting tier 0 projects. So something that we previously had to push for the European or even US supercomputers. So we have a national capability of supporting those computing cases. But at the same time, we have a world's leading AI platform and these collaboration aspects that I was just talking about. And one should also remember when talking about Lumi and CSC services that CSC has grown into kind of a full stack of services what comes to the researcher needs of this decade. So we hope and we believe we have something to offer to add value for all stages what comes to from the idea to the publication of the research. So there's a broad stack of capabilities that we can offer, be they computing, data management, or like storage style capacities. And the full list is available as a service catalog under the research.csc.fi. Okay, in the last part of the talk, I wanted to start or encourage you to mentally prepare for the Lumi system. So, like I said, 1 year from next summer, we will have the system open, and 1 year from now, we will be in the full glory of the system. And so the time to start preparing for the system is already now. And just to recap the snowflake picture, so what are these capacities that should be interesting for the end users here? This is, of course, the extreme computing capability, starting from the extreme computing capacity based on the GPU partition Lumi-G and the CPU partition Lumi-C. And the underlying idea, the concept of Lumi has been from the beginning this kind of a Swiss Army knife where I can pull up some kind of a knife or screw for all workflows and use cases that the research of this decade will need. So it is, yes, it can offer this something we could call leadership computing, the highest tip of the iceberg computing, but it's not limited there. So we do welcome jobs of even serial single CPU core jobs. So it can do this kind of like extreme computing, but it also can take in the kind of like a long tail, less resource intensive research needs. And they are most welcome there. So the Q policies will be supporting jobs from even the high throughput jobs like multiple serial, many small jobs up to the jobs that consume 50% of the system, and even to full system with special arrangements. And remembering that the jobs can indeed, in fact, combine both partitions to the same workflow if that makes sense or is beneficial. But the computer capability is of course the main thing, but it's not the only thing, and meaning that there are capacities that may be the important thing as their own. So the interactive usage platform of the Lumi-D, that's the data analytics partition, is something resources we don't have to offer at CSC at the moment, but now we would, and now we will. The software stack of its own will be an asset, and also the data management capabilities based on the object storage service Lumi-O, as well as the microservices running on the cloud platform. And on a gray there is the notion that we do, like I said, we have an aspiration of adding emerging technology platform for starting exploring the future world of quantum computing. And for Finnish researcher, the resources application will be pretty, well, something you could expect. So first of all, CSC will be your point of contact for pretty much all the different project types. And these projects will be brokered in terms of like a single PI project of this kind of like a general access project. That is something that you are familiar with CSC at the moment, something just can be considered whether it may make more sense to run on the DL2021 side, Mahti-Puhti side, or Lumi. But also, like I said, we have now capability for the tier 0 extreme scale projects. That will be one of the project type there. And in addition, we grant accesses for developing scientific software and benchmarking the cases and the technical capability of different software for the tier 0 projects. And also we are working on something we called community access or strategic community access, where the allocator role is delegated for, say, research infrastructures. But that is something that we will work on later on. So as an end user, how should I prepare for Lumi? It's at least first of its kind of an opportunity in Finland. So let's strike the iron while it's hot. So let's take the most out of the system from the very beginning of the system, and then show that Just like there's a very nice resource for doing top-notch science, or at least the platform or the infrastructure is not the bottleneck for doing world-class research. So thinking already projects and use cases that would be could be benefited by Lumi capabilities. So, for instance, take cases for this kind of like a grand challenge computing projects, or adding flavors of combining machine learning into the HPC on top of HPC data, or similar kind of combinations of these different worlds. Lumi will be a GPU system, so it needs software work. But however, it will be a robust production system, and GPU programming is not very heroic effort anymore as used to be perhaps 10 years ago. But there's a very big pool already of the GPU-enabled code. So first thing to see is whether your favorite software has been GPU-enabled or not. And also minding that perhaps not the whole application don't have to be GPU-enabled. It does sufficient if kind of the most computing intensive parts of the application are. And anyway, the code modernization will be a team how to prepare for the application, especially if you are developing your own application or are contributing to a software consultant. And for those people who do develop software or at least build community software, the Lumi's programming environment will be based on the AMD's ROCm, which is an open source project mostly run by the AMD. And it consists of compilers, scientific libraries of the usual suspects, and also machine learning frameworks that the most commonly used frameworks and the machine learning libraries will be available on the ROCm stack. And it will be supplemented by the vendors or the integrators stack, the Cray programming environment. So people who were using SISU system already late and then decommissioned system SISU, you will find the computing environment very familiar. So the Cray compilers, libc libraries, CrayPath, and so on. And together with the Cray's deep learning plugin, which enables scaling the deep learning lab frameworks nicely over many nodes. And so basically summarizing the preparation or the technical preparation work is just a few remarks. So how should I, if I'm a developer or like somehow involved on the scientific software, so what should I do during the next couple of months is design how to sort of like utilize the different partitions. So where I use CPU nodes, where I use GPU nodes, of course, code modernization. So instead of legacy Fortran, there's the just like using the HPC languages as they are today instead of as they were in the 90s is something that the benefits on the modern platforms. Frameworks, libraries, looking at them, how to use them, and build code on top of them. And if you're down to the MPI level, nonetheless, just like write them well scaling MPI code first and accelerate that to the GPUs and not in fact vice versa. And if you have a GPU code already, I would assume it's written with CUDA or OpenSCC. So in those cases, in order to use the AMD GPUs, we need to do something a little bit more work, meaning that we need to port CUDA codes into something called HIP, which is AMD's re-implementation of CUDA. So it's in the simplest case, it's a search and replace of the functions. In most real-world cases, you need to do a little bit of manual work there as well. And also moving from the direct-based approach, moving from OpenACC towards OpenMP5 as the directives is something that needs some code work, but it is kind of like a not an enormous undertaking of moving to this between these two code bases. OpenACC will be supported, but not perhaps every single feature and with every programming language there is. So Lumi will come. The first phase will come with this early access or porting platform, and so that will be a place to work with the codes. Before that, in fact, you can try out HIP already now on Puhti AI. So it's an open source programming approach, agnostic to the backend hardware. So you can convert your CUDA codes into the HIP already now on Puhti and test them over there. Okay, that was the snowy journey that I wanted to preview to this upcoming system with the following concluding remarks or take-home messages. Is that we are entering an area in European computational science or data-driven science where there's an unprecedented amount of relatively unprecedented amount of computational resources and capabilities available in Europe. And in Finland, it's nicely complementary and synergistic with the up-to-date, ambitious national infrastructure. And the kind of cherry to the cake is the Lumi supercomputer, which is a world-class resource designed for a broad range of user communities, use cases of this decade. And I mentioned that the Lumi will be a GPU-based system to get this extreme computing capability, so it needs some software preparation work. But at the same time, it's not esoteric or experimental in any manner. It's meant to be there. It's meant to be operational 100% of an SLA, and with a very predictable and easy to reach performance. And in order to utilize the GPU system, some application work will be needed as discussed, but I'm sure it will pay off. And it's time to start preparing for the Lumi era already now. So thank you people on the audience. Thank you people on the online for attention. And if you have any questions, feel free to please visit our webpage on lumisupercomputer.eu. Feel free to contact us via the contact at lumisupercomputer.eu, or if something, I can also be directly reach out. And we are present also on social media, Twitter, LinkedIn, YouTube, and take a look at those. And of course, we're here in Roadshow. I think we have time for addressing a couple of questions.
Right. Thanks, Pekka, for your extensive presentation on this Lumi supercomputing facility. There's an opportunity now for grab a few questions here, and indeed we have in this Q&A box actually 3 ones. Let's start from the first. Simpa Äkäslompolo is asking that we refer to Lumi as the EU flagship computer, and the Pekka project has 3 machines, European pre-X scale. How does Lumi compare to the other 2?
Yes, yeah, it's good question. And so of these two systems, the Italian system called Leonardo has been announced. It will be a system delivered by Atos based on the NVIDIA A100 GPU technology. The Barcelona system hasn't been announced yet, so the procurement is not complete in Barcelona. The important factor, thank you for bringing this up, is that EuroHPC, the commission share, so the 50% of the resources share applies to all 3 systems. So a Finnish researcher can apply the EuroHPC resources from these 3 machines, including Lumi, from the commission share. So basically applying for praise projects, you can direct it to some of these 3 systems, including Lumi. And in addition to that, there are the national resources. So we have the Finnish share of the 25% of the Lumi resources is the Finnish one. So there's like now multiple channels for getting your computational quotas.
Anything related to the performance of between these machines? Of course, Barcelona was not announced yet.
Yes, Barcelona hasn't been announced, so these 3 systems will be a little bit of different in profile and architecture, which is of course a good thing for having a diversity of architectures for different kind of use cases. Lumi is, I recall the Spanish, the Bologna system, so Leonardo, to be roughly 300 petaflops. So Lumi will be some like a 1.5 to 2 times faster than the Italian.
All right, thanks. Hopefully that was adequate response to the first question. Second one we have here from Mikko Hakala. What are the limitations and recommendations for more sensitive data processing, personal data and anonymized data separately? And can those be processed at Lumi?
Short answer is yes, but so we are working. We have this kind of like one of these swimming lanes that we are working on at the moment for building the user environment. There is the support for GDPR compliant or subjective data, sensitive data. It's going to be based on encrypted file encryption and containerization of the data. So we are building the stack at the moment together with the Elixir community within the Lumi consortium. So it will be there. However, at the moment I don't dare to promise from the day one, but it's a definite theme that we have identified, resourced, and we are working on towards to provide this capability on Lumi.
All right, good. So answer is yes, but
yeah,
when? Yes.
But so it will be there in the early stages of Lumi, so you don't have to wait to the end of the life of the system. So it will be there, but I don't dare to promise still next summer. But
correct. We have still time for I think this third question from Simppa Akaslompolo as well. Will the Lumi G nodes have significant CPU power in addition to the GPU? And does one need to implement codes that use both the CPU and GPU efficiently to gain the bulk of performance?
No, that's not the idea. So you are the CPU will be there just for orchestration. So you are not you don't have to write code that utilizes both for getting the oomph out of the node. So it's a GPU code with the shared address space across the GPUs and the CPU, and the CPU is there for only for the orchestration.
Okay, thanks. At the moment, we don't have any other questions on the line. So would you like to see the chat? So please, you can still shoot us with questions until we have this specific Q&A session later on today, starting at about 11 o'clock. So room is free for that. And now we try to show one more video to you before we go to the break. See how it se toi linkki.
Hei, mä oon Anna-Maria Henel ja mä oon yksi startup-yritys Dciorin perustajista. Dcior on helsinkiläinen ja suomalainen yritys ja me tehdään ohjelmistotuotetta lääketieteellisten kuvien analysointiin. Tällä hetkellä näitä kuvia yleensä katsotaan 2D-maailmassa ja sitä analysointia tehdään pitkälti käsityönä. Ja meidän ohjelmisto mahdollistaa automaattisen kolmiulotteisen matemaattisen analyysin näistä kuvissa olevista kudoksista. Ja tätä tietoa lääkärit, kirurgit, radiologit käyttää mahdollisimman hyvän diagnostiikan ja hoidon ja leikkausten suunnittelun tekemiseen. Meidän teknologia perustuu vahvasti matemaattiseen mallinnukseen, analyysiin, tekoälyn käyttöön, simulointiin ja optimointiin ja sen myötä mahdollisimman hyvä ja tehokas laskentakapasiteetti ja datan hallinnan infrastruktuuri on meille tärkeää. Ja tämän kautta tämä Lumi-järjestelmän tulo Suomeen avaa meille täysin uusia mahdollisuuksia, mitä me voidaan käyttää. Meidän yrityksen kannalta kansainvälinen yhteistyö on ensiarvoisen tärkeää. Me tehdään sitä myös lääketieteellisen tutkimuksen osa-alueella ja tämän meidän teknologian osa-alueella. Ja me odotetaan innokkaasti, että tämä Lumi-järjestelmä tulee meille tänne Suomeen.
Good. That was greetings from Anna-Maria Henen from Disior about the opportunities that supercomputing overall brings to the commercial companies, and now waiting eagerly for Lumi benefits as well.
For other similar testimonials and comments, you can visit the Lumi YouTube channel for different perspective from research and different stakeholders.
Good. Now we are at the end of part one. We have now a short break. We commence 10:15 with another presentation. So please be online, ladies, at that time. Thanks. Hello all, welcome back online to this Lumi Roadshow event in capital area Finland. Next, we will have a presentation from Milica Todorovic, research fellow from Aalto University, giving a research perspective to supercomputing and talking about her research area. Please, Milica.
Thank you, Pekka. Good morning, everybody, and welcome to this event today and to my presentation. So my name is Milica. I'm a research fellow at the Department of Applied Physics at Aalto University. And today I'll be telling you about how we combine material simulations with artificial intelligence and how we do this with high performance computing resources. So the outline for today is the following. So I will start by introducing computational material science. And then I will tell you a bit how we use AI with it. I will cover 3 case studies. One where it's classic data-driven science. One where we use the AI to drive the workflows, so AI-driven science, or what is known as active learning. And then I'll talk about some cutting-edge research that we're doing with FCAI on human-assisted AI in material science. And I'll finish with a topic that we're all increasingly interested in, is how to use AI in experimental material science. So let me tell you a little bit about my background, history, and my HPC timeline. So I'm not from Finland. I grew up in Serbia, but I studied physics at University College London. And then I moved to Oxford to the Department of Materials to complete a doctorate. And after this, I moved to Japan, which was my first experience with high performance computing. I worked at the National Institute for Material Science, which had its own supercomputer. That was quite a luxury for me at the time. And my group was developing large-scale material simulations. So at the time they worked a lot on the Earth simulator, and they were in charge of planning and purchasing for the K supercomputer. They were one of the pilot groups for K supercomputer, and they used it for a long time now. This is, of course, a retired facility to make place for Fugaku. So all of this HPC experience came in handy when I came back to Europe to work at the Autonomous University in Madrid in Spain. And there I was a big user of the BSc and Mare Nostrum. I used Mare Nostrum 3 and 4 a lot. On tier 1 level, I used Praise and the Curie machines at tier 0 level. So I had several preparatory calls and 1 year-long tier 0 full project on Curie. That was very interesting. And when I arrived in Finland in 2015 at Aalto University, I started being a big CSC user. We managed some grand challenges here. So this, I would say, is what kind of all led to this moment. Now, when it comes to HPC and my research, I'm very serious about it because I feel that one of my jobs is literally to save the world. Currently, we have a lot of global challenges like climate change, food production, sustainability, green energy. All of these are challenges of today, and we need to develop technologies for the future to tackle them. And this is where material science comes in. The primary role of material science is to find better material solutions for the technologies of the future. So we simulate, for example, optically active molecules for organic optoelectronics, and these can serve for tomorrow's TV screens. We look at phase change memory for your mobile phone batteries. We look at wood-derived biofuels for sustainability. We look at next generation organic and inorganic solar cells. So these are some of the work that my group does. I'm in the CEST group at the Department of Applied Physics at Aalto. Here, this is us maybe about a year ago. CEST stands for Computational Electronic Structure Theory. And this group was started by Professor Patrick Rinke 6 years ago. And since then, we've become pretty embedded in the Finnish national system. We've run 3 Academy of Finland projects. We have 2 Academy Research Fellows, 3 Academy postdocs. Currently, we're 17 from 4 different continents, so very diverse group. And we also have several subgroups with complementary research lines, and we collaborate a lot. So what we do in the CEST group is study electronic processes and materials. And our main tools are electronic structure material simulations. The kind of properties we looked at are internal structures of materials, band gap, electronic states, levels of electrons, spectra, transport. And when it comes to type of materials, we'll mostly look at the nanoscale, and we'll look at anything from solid state to biomolecules. So here you can see some examples from our group's work. On the left are some organic thin films that I'm studying with Oliver Hoffman, and we're looking at how organic molecules form first layer and then the second layer against a crystal, and this is important in a lot of devices. We look at perovskite solar cells. This is a research line led by Jinghui Li in our group, who recently became a professor in Xi'an in China. We look at ligand-protected nanoparticles, and Xi Chen, my colleague who's an Academy Research Fellow, is the subgroup leader for this work. So really quite diverse materials. Of course, high-performance computing is really instrumental in this process. Our key tool is density functional theory, but we also use beyond DFT methods in quantum chemistry. The codes we use are standard in the field, from FHI AIMS, VASP, and so on. These are standard packages, and they rely on some standard libraries freely available in our systems. When it comes to CPU size that we use, it varies quite a lot. Some smaller systems like this hybrid perovskite words of Jinghui's, that can be run on something like 64 cores. Our colleague Thomas Rossi, who's an Academy postdoc, he's looking at plasmonics in these gigantic silver nanoparticles with 500 and more atoms. So this requires kind of mid-level, what we call mid-level, so 500 cores or so. And then in Xi's group, Esko Makkonen was looking at these ligand-protected nanoparticles. They were very large, more than 1,000 atoms. So this for quantum chemistry and DFT is on the large side. So we need quite a lot of cores for this. Now, when it comes to accuracy levels, we have to then remind ourselves of the main challenges for us. The main computational problems and algorithms we are solving is matrix diagonalization and inversion. And this requires large memory. So shared memory machines are important to us. And there we are always struggling with the parallelization bottleneck of how to distribute this memory across different nodes without suffering from too much latency from inter-node communication. Now, all of this has been solved somehow reasonably for main DFT level, but if you want to then drive towards higher accuracy level, we have operations that are on top of cubic scaling matrix diagonalizations, and this makes our computational scaling up to n to the power of 7 with system size, which is for example, configuration interaction or like similar quantum chemistry methods. And this is a problem for us. Then we have to deal with a situation like this, where we want to study large systems like this molecule is orbiting on a surface, like on the left, and we can only touch this with standard DFT. And what we would really like to do is study it with GW level of accuracy, which is a much more sophisticated method. And my colleague Dorothea Goltze, she's an expert in GW, and she frequently simulates the systems like on the right, just a kind of small molecule. Because these are the kind of system sizes she can access because of the unfavorable scaling. Now, there's a lot of solutions in the pipeline. So my colleague Mark Dvorak is working on approximate solutions like this dynamical configuration interaction method, which is an embedding method trying to treat only certain important states with high level of accuracy and the rest with normal DFT. And hopefully that will allow us to treat much larger systems with higher level accuracy. But this is a problem that remains for us. That ideally, we would like to study large system with high level of accuracy, and currently we can't. And this is somewhere where GPUs can help. So traditionally, we haven't been able to exploit GPUs fully because of our large memory requirements that really call for CPUs and large shared memory. But it turns out that you can exploit combined CPU-GPU architectures. And you can let the CPU part handle the large memory required, and you can offload some expensive computations onto the GPUs, which is very efficient. So our colleagues, Dorothea and Tuomas, have been testing this now on Puhti AI, which 40 CPUs and 4 GPUs, and they've been using the FHI Ames DFT code with hybrid DFT and GW levels. And with very small molecules, they were able to establish that if you offload certain operations onto the GPU, you can achieve a 4 times speed up. And so while we are really unable to fully utilize GPUs for quantum chemistry, this kind of combined GPU-CPU architectures can help us in the future to drive our software into a situation where we can hopefully tackle these very large systems like Tuomas's plasmonic nanoparticles with high level of accuracy, which is so far inaccessible. Now let me talk a bit about data science and artificial intelligence. So I'm in charge of our subgroup for these activities. And of course, this all became possible when the materials data structures became available. Here we wrote a review article about this, and here we show a timeline of the data infrastructures. So started in 1965, there's been a notable speed up in the 2000s when the hardware and storage capabilities were boosted. From 2010, already the US had the major data infrastructures in place, and in 2015, Europe got its own. This is the NOMAD Center of Excellence, in which our group was one of the PIs, and so was the CSE. They were really instrumental in setting up this infrastructure. So now that all this data became available, AI became more important in material science for one key reason, and that is that AIs can infer patterns in the data much better than what humans can do. Some of the ways that AI is currently used are for fast prediction. So this is great for pre-screening. You can also use it for materials optimization and refinement. So this is to refine the materials we already have, or you can use it to search for materials, designed to search for materials we would like to have, but we don't yet know about. And of course, the previous optimization is an interpolation problem, and the search for new materials is an extrapolation problem, which is much more difficult for the AI. Generally, there's a lot of impact to be had. With AI, we can bypass a lot of costly experiments and calculations. We can move the discovery away from intuition-led and trial and error-led procedures and accelerate it. And generally, we can use it to optimize procedures. And if you want to know more about it, we are running a machine learning for the material science course at master's level in the Helsinki region. So I'm going to tell you different ways about applying AI in our group. Case one is what we call classical learning, or classical machine learning, where you have a data set pre-computed and you can use it and apply machine learning and get some result. Case two is something more advanced. It's where you exploit the learning of the AI model to help you select your data. And that turns out to be a lot more efficient, but also the workflows are more complicated. And I'll tell you about that. And then The last case is human assisted learning, where you let the AI sample not only data, but you sample the scientist at the same time. And this is some very new trends in AI. So first, the classical learning applications. A typical thing to do is to map one property of a material to another, and then to use the trained AI as a fast predictor. So in this case, we looked at the structure of small molecules, and we mapped it to some electronic structure property. So in first case, the property were the levels of electrons in the material, and this is related to the way they absorb or emit light. And we used kernel ridge regression for this. We ran it on a grand challenge. And this was kind of standard work. In collaboration with Aki Vehtari at FKI, we also trained the AI to map molecular structures to entire optical spectra. This was done with neural networks. And this caused a bit of a splash, and even Samsung called us because they are constantly looking at AI-based methods and new methods for pre-screening promising molecules for their TV screens. Now, there are some pros and cons with classical learnings when it comes to HPC. The good thing is that the data generation and the AI learning are well separated on HPC platforms, and the data can be done with high throughput workflows, which are very well developed. CSC has a very good setup for this. And then the AI can be done exclusively on GPUs, which is a huge acceleration. So we tested, and it's about a factor of 100 on GPUs versus CPUs with neural networks. So this is all possible to do with the technology we have so far. The con is that we've realized after several years of doing the classical machine learning that not all data in the data set is informative. Some data sets have too many similar entries, and this leads to redundancy. Some amount of redundancy is good for machine learning because it accelerates, improves the learning. But after a while, the machine stops learning, and you just keep putting in more data, and it does nothing. Well, it doesn't do anything. It blows up the model size. In fact, it slows down all calculations, and this is also data that is wasteful to compute. So here is a result where we studied one of the data sets that we've used 2 years ago in a paper, and we have realized that about 30% of the data set was entirely redundant, and we could have removed it and had the same quality machine learning. So I feel that data curation strategies is something we should be thinking about in order to better exploit the existing computational resources. And this is something that AI learning can help with. So here I want to show you one way of doing AI learning, we do with Bayesian optimization. And something that's very typical to active learning is you have to start with a little bit of data, and then you have an iterative loop. And the first thing you do is you build an AI model. So in this case, we're using GPR, so Bayesian regression with Gaussian processes. And after we've built the AI model, this helps us then build an acquisition function. And the acquisition function tells us where to evaluate the next point for maximal benefit or for best learning of the model, for best improvement. And then we evaluate that point, we add it to the data, and then we iterate until the AI model pretty much converges, and this can be seen. So what we get out of this is a complete AI model, which gives us a kind of a surrogate model landscape of typically some property or energy across a design space or a search space. And this can help us determine what are the minima, the maxima, where can we find properties of a particular value. So this is a very good method for global phase-based search and for global optimization. And it's completely automated, so human is out of the loop. We were so impressed with what these algorithms can do that we packaged it up into our own software called Bayesian Optimization Structure Search, or BOSS. This work was funded by the Academy IPSC grant, so AI for Physical Sciences and Engineering grant. And this code is freely available to use to entire community, also the experimental community. So here is how BOSS works in practice. So here we were trying to find the best absorption geometry for C60 on top of titanium dioxide. And the best geometry is the one that has the lowest energy as a function of molecular rotation and position above the surface. And the way this works is that on the left, you see BOSS taking acquisitions and looking at these structures and noting their energy. And then at the same time, it builds a model about the energy, and from it extracts the global minimum location. And that's what the image on or the movie on the right is showing. It's the prediction of the optimal absorption structure. And you see that very quickly the prediction stops changing. So BOSS has established well what kind of absorption configuration this is. Now, there are, of course, some pros and cons when it comes to active learning and HPC. It is a much better way to collect data with active learning or letting the AI choose your data points because you can achieve the same quality learning with much fewer data points. So you don't have to evaluate nearly as much. And this is very good for costly computations like we have sometimes, and also experimental data. And another big plus when working with surrogate models is that you end up with an interpretable landscape that you can kind of attach physical or chemical meaning to. And this also builds trust that the humans can somehow understand what AI is doing, which is much, much harder to do when you have shapeless neural networks that just spit out a result. So it's difficult to interpret this. On the negative side, we have the problem that the AI training and data generation are intertwined computationally. And currently we're running all of this on CPU resources, but this is really not optimal because then some resources are idling. So we need to develop more complex high-performance computing workflows so they can optimize resource use. And I think here it's ideal to have jobs where we can simultaneously run on GPUs and CPUs, because then you can just put the AI part of the workflow on the GPUs and the data evaluation on the CPUs, and this can go a lot more efficiently. So this is an ideal test case that we will be developing towards Lumi use. And lastly, I wanted to mention about human-assisted learning. So this is a collaboration with FKAI and Samuel Kaski, where they do domain knowledge elicitation for physics-informed AI. We're trying to do a test case where we've studied the adsorption of camphor on copper, and this is a problem that Jari has solved. And now Petrus wrote an AI active learning method to sample Jari's feeling for what is the preferred adsorption geometry. So this is kind of sampling Jari's surface science intuition, literally. And this is a photo of the two of them in action. So the main objective of this AI sampling the human is to encode the human preferred solution. And in this case, it's a solution for adsorption. So we did some tests. We identified some humans. We carried out a study on two physicists, one economist, and then one bot, so an AI. And then we encoded their preferred adsorption solutions. And then when we checked the quality of these solutions, what was important to us was to check if we use the solution as a starting point on the potential energy surface and we start to minimize it to the next local minimum, how deep is the minimum? So how good quality is the guess? And then how close was the initial guess from the minimum? So that's also an indication of quality. And you can see that the physicists generally found pretty low-lying minima. So that's the image on the left. Sorry, I can't have a pointer, so it's difficult. But then the economist also found a minimum, just not as deep. And the bot didn't do too different here from the economist. So we already know for this problem that there are multiple minima. So this is a difficult problem to crack. If you look at the iterations from the initial guess to the nearest minimum, you see that the physics people and the economist all did relatively well, not too many iterations required. But then bot did notably worse. And this is because bot was just randomly guessing, and they start with really unreasonable solutions, and it takes them a while to find something more reasonable. So here we could see that already the AI could encode the difference between a human or a bot. Even if you don't have much expertise, humans are able to find some kind of reasonable solutions to begin with. Now, what happens in this system is that this molecule is a typical hydrocarbon, but it has one oxygen. And a physicist or chemist would immediately recognize that the preferred adsorption is when the oxygen is pointing towards the metal, because metal oxides are very common and stable in nature. So this is most likely the preferred adsorption configuration. And this is something that the physicists could see, but the economist couldn't. So the economist guessed the structure on the right, which is oxygen pointing up and hydrocarbons pointing down. And this is also a stable structure of a minimum in energy, but not as stable. So with this test, we were able to find out that AI can not only tell the difference between human and AI, but it can also encode the difference in expertise in some way. Now, the pros of this is that, of course, it benefits from active learning guided workflows, which is very data efficient because we can put in extra domain knowledge into the model. So not just the data, but also the experience. It is very data efficient and can help with cases where we have biased data or not enough data. It has potentially huge societal implications. So just in terms of medical diagnostics, cancer identification, things like that. On the con side, again, data generation and AI learning are intertwined. And when it comes to integrated human queries into HPC procedures, well, we haven't even begun to think about this. Maybe this is a problem we'll be solving in the next couple of years. And here, maybe some interactive partitions could come in handy to integrate all of these different aspects of the workflow. Lastly, a few words on AI applied to experimental work. This is something we're all very interested in at the moment. And here's a project we did with Finceres, which is a Center for Sustainable Materials led by Orlando Rojas. And they were using these tannic acid colloid systems that are beneficial for humans. And they also have a lot of cool properties that could be exploited for sustainable bio-based materials. So what they wanted to do is use AI to help them engineer the morphology of particles, which is an important functional property for many applications like coatings. And they wanted to see if we can drive it from 1D sticks to 3D bodies. So they mixed this into the solution with certain base, and they could control the base strength pKa and the pH of the solution. And they created some samples, and then they measured the shape of the particles. And this is the data that we used to build some kind of a model for morphology. And this is how it looks like in the search space of pKa and pH. And there are some clearly defined regions. So in the top right is a 1D region, in the bottom left is 3D particles, and you can kind of, by changing your pKa and your pH, you can go across 1D to 2D to 3D. Now, if we look at the predictive power of this model, this is how it looks like, overlaid with their actual samples. So in the 1D, you see that all the particles are somehow needle-like. In the 3D region in the bottom left, you can see that the 3D particles are kind of domino-shaped and cube-like. And then in the 2D region, there's a lot of platelets. That's some mixed morphology in green that is both 3D and 1D. And generally, the kind of 1D region, the mixed between 1D and 2D registers is very, very short 1D, kind of matchstick-like. And then we also verify this against some morphologies that were not included in the model, and they were all kind of correctly placed in the 2D, 3D regions where these particles grew together. Now, AI has huge potential for use in experiments and industry, and AI-guided product development can eventually replace the trial and error industrial procedures. But we have one big challenge, and that is data digitalization. There's just a lack of procedural standards, no quality control. We have huge problems with metadata because this is something we absolutely must encode and may be used in AI procedures. But the experimentalists don't really know what metadata should encode, and they want us to tell them, but we don't know their experiments, so we don't know what's relevant. So we have to talk a lot more about that. There's a lack of technical solutions and storage capabilities to integrate both metadata and data together, and just general lack of awareness about good practices. So I wanted to end my talk here and summarize. Definitely, HPC platforms are driving the progress in computational material science, and there's a healthy feedback between advances in computational material science and improvements in HPC architectures and capabilities. We've identified several cases of clear need for mixed CPU-GPU jobs. Partly, it is the fact that we can use GPUs to offload expensive operations while exploiting the memory of CPUs that will help us to simulate larger systems with higher accuracy levels. And also when it comes to AI blended machine learning, then these new workflows will help us offload AI to GPUs and keep the data evaluation on the CPUs. Certainly, data digitalization remains a challenge in experimental work, and this is something we have to consider more. And HPC platforms of the future, I do believe, will facilitate research into future technologies. I will end here with a small wish list for Lumi. I've spoken to my colleagues, and this is what they all said. They wanted more user training, and I think our event participants are asking about this as well. And we've already heard about this from Pekka. Extended pilot schemes, grand challenge projects to facilitate transfer to T0 computing. And it would be also great to have some user meetings on HPC in the Finnish community. We are many users, and in Japan, I attended several such meetings dedicated just to computational science and algorithms. And this is something that could be useful also in Finland. Thank you for your attention.
Thank you, Milica, for your very interesting presentation and really talking about how your research will benefit from HPC and AI and all kind of combinations and the challenges with big data as well. So are there any questions to Milica's presentation? We have received some new ones for Lumi, which are reserved likely to this Q&A session after this one. So anybody willing to have a question on Milica's research area or anything related to that? Okay, I can see none in particular. So you are very nicely listing the wish list for Lumi. And my question would have been that what is your expectations for Lumi bring in addition to what you get now from HPC? And did you see actually in this Pekka's presentation anything that would like meet your needs in your wish list? Are you hopeful that that all these what you have in the wish list will be fulfilled when Lumi arrives?
Yes. Of course, we have to do a lot of preparatory work. One important part is to make sure that we are able to switch from CUDA to HIP when it comes to switching our work away from NVIDIA into AMD GPU chips. And we have to do a lot of algorithm development, because one thing that is very attractive to us is that we will be able to use multiple partitions in the same job. And this is something that we can't do at the moment. When we use Puhti AI, we are kind of limited by the architecture of the setup, and we can't access the rest of Puhti. So I think what will be interesting with Lumi is being able to combine the different partitions into different workflows, and perhaps in some unexpected ways as well. This is why I list here added value of new resource combinations. This is something that has not been possible on previous architectures, but with Lumi, this might open more possibilities that we're not even thinking about yet. So that, I think, for me personally, is the most exciting part of the system.
Good. I'm just trying to pick up some questions from the Q&A box, which are related to your presentation. I think that there is one from Cecilia Ayala. So in the human expertise experiment, did you do more than one run of the experiment? So did the humans versus bot only make the initial guess for one experiment or more than one? Was this clear?
No, we did statistics. If it's not statistics, it didn't happen. Yeah, so we did multiple experiments and we computed averages.
Okay. Good.
Good question.
So I think that's all by now. Thanks, Milica, once again for your presentation. And what we have next online, we are picking up your questions and providing answers. Pekka, could you join us here? Just 1 minute. Maybe change the screen. All right, back online. We have some technical problems to share the screen. So please send us questions to the Q&A. Actually, at the moment we have quite many of those there already. So let's pick up one by one there. First one is from Nitin Shoni, asking about training. So are we planning any training programs for graduate students to learn how to use Lumi?
Yes, of course. Lumi, we recognize the importance of like an elaborate user program, and this time we have really resourced and ambitious and user program. Juhani is leading it, so perhaps I don't know if you want to answer it yourself. So sure, we have like a different kind of training events coming up. Target group is ranges also with the varying like prerequisite and learning outcome profiles of the workshops. Some of them will be provided by the system vendor. Some of them will be provided by the user support team. Some of them will be provided now at CSC via different kind of training instruments. And would like to already advertise the Praise Spring School that will take place in Kajaani next May, which is a kind of like a contains different kind of science case talks and also hackathons on either GPU programming using AI in science. Or like a GPU application enabling hackathons. And so it will be in Kajaani, so it will be a chance of seeing the Lumi system already. And then, do you want to continue on the training activity?
Yeah, work is ongoing, and of course the need obviously seems to be, and the target is to fulfill that need, that there are various like a type of trainings from like a basics of HPC and Lumi up to the like code optimizing, more specific training events. So everything in between, but work is like started and ongoing towards that target.
And also thank you, Milica, the previous speaker on the wish list for the training. Those were really good ideas and already partly on the menu, and I definitely will look at including those teams to the workshops.
Good. All right, next question here is from Simppa Äkäslompolo about AMD Instinct. On availability of AMD Instinct to prepare for Lumi, AMD published MI100 today. Is this the hardware or similar to the hardware we expect for Lumi?
Yes. So that's the previous gen GPU, and that will be on this early access platform that comes together with the Lumi first phase, and the Lumi itself will be on the second generation of that same line.
Okay.
So, but if you get an MI100 on your hold, you will be having a plotting platform of your own. But CSC will provide that on latest on the together with Lumi. Lumi installation. If we could have a kind of view on the Puhti or something is something we need to look at. But when at large, they will be the MI100 will be available on the first phase of Lumi.
Yes, and there was a continuation part of this question I missed. I would hope to gain access to relevant cards as soon as possible. So.
Yeah, hoping to answer. And we will get also like access to something that we cannot that is also for like a CSC internal use, but we can collaborate with customers and run benchmarks that are relevant to them and things like this. So we can collaborate on the codes even before the Lumi first phase opens.
Happy to see so many questions here now. Next one is Simo Tuomisto. Are there going to be upcoming courses on ROCm from Praise or CSC before the first phase of Lumi is launched? ROC was
this the AMD stack. Yes. Don't have a date in mind yet, but yes.
Okay, so sometime maybe with the time.
In the spring time, we plan.
And here's Simppa again. Very many good questions. Will the Lumi G and Lumi C share a fast interconnect InfiniBand level?
Yes.
Simple answer.
So it's the slingshot, gray slingshot interconnect, and they are sitting in the same interconnect, the nodes.
Then Simo Tuomisto is asking about curated data sets. Are these made for Lumi going to be publicly available if the license of the source data sets allows for it?
So we, at the moment, so it's something we can take user input. Happy to take user input. So what data sets you would like to see there is something we can then like see working on. And so it's likely it is something that data needs to be open data and something we have like a permission to take and publish. But the idea is that not everybody needs to download like big reference genomes into the system and have it multiple copies there and different versions. But there's like the kind of like a version control and the data like a verification will be done by the as in a similar fashion as we install software to the system. So we would be availing this different kind of like a most used reference data sets. So, like I said, we are happy to take input on what people would like to see there.
Yeah, that's a very good point. So you can still influence.
Yes, and not still, but during the course of the work. So we take requests.
Yeah. Then Keijo Helianko is asking about, will there be a way for Lumi users to share experiences across the different countries involved? And continuing, I am expecting that many countries will use the same software libraries that need porting, and sharing the effort across all the involved countries might make it more efficient.
Don't have a direct right away plan at the moment. Something we can definitely look at, and having some kind of like a user forums being organized, and whether they are virtual events, physical events, or user forums, it's something we can we need to think about. And also we've been envisaging of opening up like a different kind of chat services for the users that kind of like interactivity, user support, as well as each other. And things like this are on the menu. But let's see what are the kind of things that the users find most useful and convenient. So yes, but let's see how do we want to implement this.
Sure. But likely the expectation that many countries will use the same software and so on. That's
yes, of course. The user environment will be the same for regardless of the affiliation. So everybody who get an account will see the same Lumi.
Yes. Then we have a question from Simo Tuomisto. About flash storage. Is the flash storage pool going to be utilized automatically, or does the user need to request for quota on it and manage transfers files between data pool and flash pool?
The exact implementation is not set to stone yet. It's everybody will have basically quotas on each of the storage systems, so they consume the storage hour billing resources. At the moment, the thinking is a kind of like a separate I/O, like there would be kind of still like a separated from the cluster, so the data is either of them, and so it's not an automatic cache, but it's just more like a separate mount point.
But details are still to be defined. How
details will be defined, and the practical use instructions will follow.
The next one is Ilpo Vattulainen, and he's stating that one of the key benefits of GZ Grand Challenge projects, I guess, is the possibility to have separate queues dedicated to Grand Challenge project members, which speeds up the project work. However, when Lumi will start operating, it's likely that the computing capacity available will be larger than the demand. And given this positive situation, can you comment on the main additional strengths of taking part in the Grand Challenge project scheme?
The details of the usage and the project ones are to be seen. So whether there will be grand challenges per se, so there will be this kind of the part of this extreme computing project. This is more like just like it would correspond more to the praise tier 0 access than the CSC's grand challenge per se. So it is more or less on the kind of like a volume of the size of the grant. And if there's some special arrangements they needed, so they are not necessarily needing the grand challenge status. So if we need to do, the idea is to sort of avail windows every now and then for this kind of full machine hero runs, but those sort of don't need a specific like a status, but it's something that can be available for people who are interested on say such an like a exercise. But the positioning on the existing CSC's grand challenges and the Lumi's user projects is still in progress.
Okay, hopefully that was complete enough for this grand challenge, why to be there, and what addition Lumi will bring to that one. Simpaikas Lompolo is talking about software. You highlighted about OpenCC transfer to Open MP 5.0. Is there commitment from HPE to actually provide a compiler that supports OpenMP5 for AMD?
Yes, there will be at least the AOCC and the GNU compilers together with the Cray compilers will be OpenMP5 supporting the target directives of the OpenMP5 by the time of the Lumi.
Great. Nitin Shawnee having a second question, saying that this may be naive and speculative, but do you think the new Apple M1 chip architecture, Apple M1, and its future variants would be an emerging alternative to AMD for HPC in the future? If so, what implications might it have for future generations of Lumi, and how might users have to reflect code to be ported to such a new architecture? So looking maybe quite much ahead of
that's
current situation.
This is more or less like a more general on the ARM-based CPUs as in HPC. I think there are better HPC processors on the ARM family than the one referred there. So I think the Fugaku's, especially for HPC done for the tailor-made HPC processors on the Fugaku supercomputer is much more viable HPC processor than the Apple's, and as well as the European processor initiative and the REA or the API processors are something that are more closer to the HPC world. But I said then what they will be likely ARM-based HPC systems also on the Euro HPC umbrella. We at CSC or the Lumi successor or anything, we don't have any of these on the menu.
So focus is now for this current.
Focus is to get the most out of the current infrastructure.
Absolutely.
And of course, there will be time for planning to success of Lumi, but that's sort of fun.
Yeah, Lumi will stay until 26.
End of 26, and
end of
of course
26.
there will be time, but it will be a new times and a new world. So let's it's good to look ahead, but not too far ahead.
Right. One more question in Q&A at the moment. Still, you have opportunity to send more because we have still time to shoot questions to Pekka and others us here. Simo Tuomisto is asking about follow-up on the curated datasets. Are the curated datasets going to be shared in an open source fashion so that other sites, universities, etc., can utilize the same APIs formats. This would make it easier for research to replicate models results on other systems.
I believe in the spirit of if you use open data sets, I mean, they also the kind of like a derivatives if that will remain open.
Okay, so assumption is that this seems to be possible. What is
and likely even the data licenses will like a require of like a keeping the data open. So
yeah, excellent. Yes, happy to see so many questions in this session. Do we have any more? Not at the moment, right away. So we are a bit ahead of time. Obviously, nothing from the audience. No raise hands. Can you see any? No. Okay, that was a quite a big bunch. So I said this event is recorded and will brought to availability for a certain amount of time after this event. So it's possible to at that time come back to these questions and answers there. And if something was missed, right online. If you can share this next slide, okay. So coming towards the end of the session of the event, here some reminders of the social media for Lumi: Twitter, LinkedIn, YouTube addresses, and also CSC, who is hosting this event, and Lumi Supercomputer. Pekka has something to.
Yes, so there's also the Lumi webpage. You can find like a blog post on more technical deep dive into the programming environment of Lumi, and we will continue the blog series with also in kind of like experiences and best practices and like a material on the we're porting the code base from to the open standards.
Yeah, so it's findable in this Lumi Supercomputer web page that is shown there, and actually it's quite fresh. The first blog was last week, announced last week.
2 weeks ago.
Yes, released last week. And if we go to the next page, so we'd like to thank all of you for active participation to this capital area Lumi Roadshow. Thank for the presenters, Pekka, Milica, excellent. And if you have any further questions, please send your questions to contact@lumi-supercomputer.eu. And you can stay up to date with Lumi by subscribing the Lumi newsletter. And there's an address for that. And follow us in social media. And please remember to give us also feedback about this event. You will receive a link to a short questionnaire per email, most likely already today, latest tomorrow. So thanks all. We conclude now. Bye.